Tonight we're trying to find integer solutions, x and y, and we'll just write down x. I forgot to write this down. X, y is a member of z. The integers. Okay, now it's supposed to equal to a prime, some fixed prime minus 1. P is a prime integer, divisible by 1 in itself. That's the definition of a prime. Has no divisor strictly between 1 and itself. Now we're trying to show that there are no ordered pairs x, y that are just natural numbers. Just to give you an example of what I mean by that, 0, 3. You know, the natural numbers are just the positive integers. 0, 3 is not a member of n cross n. You know, it's the Cartesian product of the positive integers. Okay. And, but 2, 6 would be, okay? N cross n, okay? So we're trying to show that if you have this constant on the right-hand side, a prime minus 1, you will have no positive integer solutions for both coordinates, all right? So let's get down to business here and see if that's true. So the approach here is slightly unmotivated, but you'll see why I'm doing it fairly quickly. I add 1 to both sides. And the reason why I'm doing that is because we get a common binomial factor. It'll help right here. I'm going to go ahead and envelop the y plus 1 in parentheses and put a 1 here. And the 1 you see right here is the same as this 1 right here. Okay, so in other words, we have a common binomial factor of 1 plus y. We can factor it out and we get this statement right here. Okay, so we have 1 plus y, and again, remember y and x are supposed to be positive integers. So what we can do right here, because p is prime, p is either equal to 1 times itself. We'll write 1p for emphasis here, 1 dot p. Now also, and we'll see this doesn't make any difference, or this won't yield the type of solutions we're looking for. P is also equal to minus 1 times minus p. And I'm not going to work that case out completely because it's obvious that this case will yield negative solutions, solutions that are not in n cross n, okay? So from here, it's very quick to see what's going on. We can write down x, y, the ordered pair x, y in terms of p. So you can see right here that x would be equal to, if you subtract 1 from this, p minus 1. So that would be positive. P minus 1 is a member of n, but notice that y has to equal to 0 for this to hold. Now you can see that this never would happen if p was a composite number, because you would have a divisor that wasn't equal to 1. Okay, so there you go. And also by symmetry, the very same thing would happen. You could another solution would just be swapping these. Okay, if we flipped around these assignments here, x, y would be equal to 0, p minus 1. You see, these are going to be the only possible positive integer solutions, and one of them is not positive, right? And folks, again, I won't go through it, but if you set both of these equal to, if you set this equal to -1 and this equal to negative p, you would have negative solutions here. That's crystal clear, right? If both of these were negative numbers, then you would have negative solutions, okay? So we've actually finished the proof right here. Now, a concrete example would be if p were, let's say, 17. If p were equal to 17, the solutions would be 16, 0, and 0, 16. I mean, those would be the closest things, the closest solutions to having a member of n cross n, right? But again, neither one of these are a member. Okay, I'm almost out of room here. Neither one of these are a member of n cross n. Okay, so we have proved what we set out to prove. I can write QED above that, I suppose. Okay, folks, that's what we've demonstrated. And that's the end of that, folks. No solutions for this integer equations that are positive integer coordinates, each of them being a positive integer coordinates. Okay.